So today we'll continue with the construction of the nonlinear theory of gravity. So where we wanted to, so we are talking about nonlinear gravity. So we said that we found some guiding principle, which was to construct a theory which is generally covariant, and such that in the linearized limit it reduces to what we already had for a spin to gravity. And so the route that we were following was that we were trying to construct this action which is generally covariant, or it is invariant on the diffeomorphisms. We divided the action into two parts: the gravitational part that only depends on h mu nu, and the matter part that depends on h mu nu and the matter field. And then we started discussing what are the rules to construct this matter action. So first we focus on matter field. So so far we discussed two of the rules. We said that we combine h mu nu and eta mu nu, the Minkowski metric, into one metric that transforms like a tensor, like a rank 2 tensor, while neither eta mu nu nor h mu nu transform like a tensor. This combination does. So we use this metric g mu nu and its inverse to construct our matter action.
And we say tensor transforming as a tensor, we mean general coordinate transforms, not just Lorentz transforms, right?
Yes. On the general coordinate transform. Yeah, under just Lorentz, they do transform like tensor. Okay, so then. So that was the rule number one. Rule number two was that when we have derivatives of vectors and tensors, those derivatives have to be replaced by covariant derivative, because normal derivatives of a vector will not produce a tensor field, while covariant derivative does. So d mu has to go to covariant derivative nabla mu, and this covariant derivative is constructed using essentially the derivative of this metric that we constructed, or derivative of h mu nu, in a very similar fashion that we construct covariant derivatives in gauge theories, like in U1 theory. So for instance, and it also depends on what it acts on. Again, that shouldn't be too surprising. For instance, in the U1 theory, we have the covariant derivative d mu acting on some field psi. We say this goes as d mu plus I q a mu times psi. But this q depends on the charge of the psi field. So if we consider fields with different charges, the covariant derivative will differ. More sophisticated way of saying it is that this covariant derivative cares about what representation of your symmetry group psi lives in. And that's this charge q in this simple example is responsible for determining what representation you live. Now here is a more complicated version, when I act by this covariant derivative on a vector or on a tensor field, it will have different expressions because vector and different tensors with different ranks, they live in different representations of our symmetry group. So, for instance, if I just write the derivative of a vector field with upper index, then this will be d mu v nu plus gamma nu mu lambda v lambda. And then if you consider other objects like covariant vectors or tensors, then there will be either the sign changes or you will get more Christoffel symbols. The formula for it you can find in the notes. Essentially, for every index you have one extra Christoffel symbol, and this Christoffel symbol, so this is like the analog of our gauge field connection, is given by derivatives of the metric. Whenever I don't even need to write d mu g alpha lambda plus d lambda g alpha nu minus d alpha g mu lambda. Okay, so this was rule number 2. Replace normal derivatives with covariant derivatives. And then there is a rule number 3 that we did not discuss, but we'll discuss now. And this is to replace the measure of the integration that we have in the action to the invariant measure. So usually we write d4x times some Lagrangian, where the Lagrangian is a scalar quantity. Now, since we are allowing general coordinate transformation, then this is not invariant anymore on the general coordinate transformation. Well, because the volume elements can change. If, say, the simplest thing is, for instance, you can imagine I rescale all of the coordinates by a factor of 2. Then this measure will change by a factor of 16. So what we should do is to replace this with a new invariant measure, which is d4x times the square root of minus g, when this square root of minus g is really a shorthand for a square root of minus determinant of g mu nu. Now, why is this measure invariant now? Because so let's see how does this d4x transform. When we do a coordinate transformation, then this d4x has to go into d4x tilde times the Jacobian of dx tilde, where the Jacobian is just a determinant. So this Jacobian of dx with respect to gx theta is just a determinant of dx mu. So this is a 2-index tilde. So this is a 2-index object, is a matrix, is a 4x4 matrix. We take the determinant of this matrix, that would be the absolute value of that determinant is the Jacobian. And that's how the measure changes. So what this square root of g does is that it changes in exactly the opposite way to cancel that, so that this expression for the action will be generally covariant. And to see this is very easy. We know that g mu nu times dx mu dx tilde alpha dx mu dx tilde beta is equal to g tilde alpha beta. So if I take the determinant of both sides of this equation and use the fact that the determinant of product of two matrices is the product of the determinant of A dot B, where A and B are two matrices, is equal to determinant A times determinant B. So if I use that, I will see that G transforms in exactly the opposite way, or basically it absorbs this Jacobian fact. Okay, so these are basically all of the rules. So we are basically done with the construction of a generally covariant matter action. And then we can proceed to the gravitational part. But before that, one thing that one observation to make is to derive some covariantly conserved energy momentum tensor. So let's see what we have done. What we have done is that we have constructed an action, a matter action that is invariant under diffeomorphisms, right? So it's invariant under x mu going to x tilde mu equals x mu minus some x sin mu. So the action that we constructed is and this xi is a general function of the coordinate, which we might assume to be first of all infinitesimal, and secondly we can assume that it goes to 0 at infinity. So what we have constructed is some action that is invariant under this transformation. So delta xi of this S matter that we have, which depends on h mu nu. Now instead of h mu nu, I can write g mu nu, because the difference between two is just a constant matrix. I'm just choosing a different variable to represent the dependence on h mu nu. I'm not doing anything non-trivial. So what we have is that this variation is equal to 0. But that's basically, that's the goal of these three rules, to construct some action that is invariant under those variations. Now we can look inside this action and see how this happens. So if I look at this action, how is it written? It's written as it's written in the following way, right? This is an integral of d4x, and then when I do this variation, there will be variations of the metric and the variation of the fields under this transformation. Yeah.
We said at the beginning, if we can divide the action to two parts where contain only like pure fields, we can this time take one part and take a conserved quantity for each part, which will be separate. But here they are coupled. So how we are taking conserved quantity for from coupled field, from coupled terms, for only one part of the action, not the whole the graviton part of the action.
Well, you will see, because at the moment I haven't really accomplished anything. I'm not going to use the Noether theorem here. So if you are worried about the Noether theorem, I'm not using that at the moment. You're absolutely right that if I have the action which is made of two parts and some fields appear in both parts, like here there is h mu nu here and h mu nu there, I cannot apply the Noether theorem just to this part to derive a conserved energy momentum tensor. Neither I can apply it to that part, I can only apply it to the whole thing. But here I'm doing something different. I'm not applying the Noether theorem, I'm just saying that this matter action, not by construction, is invariant under these diffeomorphisms. It's not invariant when combined with the other part. It's invariant by itself.
So we are going to extract conserved quantity on using the fact that that part of action also have to be minimized, like both of them. So we just use this fact here. Using this, we'll use this fact.
Yes. So yeah, this is 0. This argument that I'm giving here, you could apply it if, well, you will see what are the assumptions. But the only part the only assumption that is important for my argument at the moment is the fact that this action by itself is invariant under this transformation. I do not need to combine it with the other part. And the second fact that I haven't used it yet, but I will use, is that all of the matter fields live here, but not there. So that is the second assumption that I will. Now let's see what I'm going to do. I'm going to say that the variation of the action due to this diffeomorphism comes from the variation of g mu nu and the variation of psi. So I will write delta psi of g mu nu. Again, I can use g mu nu with upper indices. This is related to g mu nu with lower indices. It's just the inverse of that. So these are not independent quantities. I can choose which one I want to use. Times the variation of square root of minus GF. Now something that I did in the notes was that I called the whole thing F. Which means that now my Lagrangian, if I call this whole thing L instead of this term, then it means that my Lagrangian is now a density instead of, is a scalar density rather than an actual scalar, meaning that if I rescale the coordinates because of this extra factor of square root of g, it will get a factor of Jacobian. So maybe, let me call it just L hat. So this L hat is now a scalar density. So for instance, to be very concrete, this L hat for a scalar field, this L hat will be minus the square root of minus g over 2 g mu nu d mu psi d nu epsilon. Okay, so now here we have what? We have the derivative of this L hat with respect to the g mu nu times the variation of g mu nu plus the variation of the fields, and this psi is now sitting here as representative for all of the matter fields times d L hat times d epsilon. And now, what is the change of g mu nu with upper indices? That is essentially inherited from the transformation of h mu nu. So once we know how h mu nu transforms, we know how g mu nu transforms to linear order in our xc parameter. So this is basically given by, this is one of the exercises, given by the covariant derivative of this parameter of transformation. So it's given by minus nabla mu xi nu times minus nabla nu xi mu.
Minus.
Yeah, both of them are. Well, this is symmetric in mu nu, so it's changed better be symmetric. Okay, so we can plug that in here, and then we are going to use some extra manipulation of this first term. So we have integral d4x. Well, let me, for the moment, don't write the integral. So let us just write this. Nabla mu xi nu times dl hat d g mu nu. So what I do is that I just do play some little tricks here. Let me first divide and multiply by the square root of g. And then I use the Leibniz rule in the following way. So I can write this whole thing as d mu del mu of the square root of minus g times xi nu dl hat d g mu nu. Sorry, no, the other way. I don't like it. Minus xi mu del mu of 1 over square root of minus g dl hat dg mu nu. So I just used we just use the Leibniz rule here, then I will recover that origin. And now what can we do? The other thing that we can do is that we can raise and lower the indices using the metric. So one property that this covariant derivative has, it's a very important property of this covariant derivative, is that it is called metric compatible, which means that the covariant derivative of the metric is equal to 0. So the way I define this, covariant derivative guarantees that del mu or g alpha beta is equal to 0. What that means is that this expression, when I have del mu with upper indices, this is really g mu some index. So this is g mu alpha del alpha as 1 over square root of minus g x I nu dl hat dg mu nu. So this index can be raised and lowered using the metric, but since the derivative, covariant derivative is metric compatible, I can take this metric inside to write it as grad alpha or g alpha mu times that. Because the derivative of the metric is 0, so I can just take it in and out. But then this expression has this general form. It is minus the square root of minus g nabla alpha of some vector field v alpha. So this whole thing is just a one index object, a contravariant vector that I can call v alpha. But this expression is equal to, so again there is another identity that holds because of the way I define this covariant derivative. This is a covariant divergence, and the covariant divergence times the square root of g is the ordinary divergence of a square root of g times more vector. So this is again an identity. Now remember that we are integrating this whole expression over the space-time. So the first term here reduced to an ordinary divergence. So if now I write if I now write the final answer for this first term, the first term becomes just the alpha of g mu alpha xi nu delta l hat delta g mu nu, and then the second term remains whatever it is. Okay, now let us plug this back in here and do the integral over space-time over d4x. When I do that, then this term vanishes because it's a total derivative that it's a divergence that reduces to the boundary term, and this c is assumed to vanish at the boundaries. So this first term gives 0, and then we will end up with minus, or let me take the minus sign inside, so we end up with integral d4x square root of g x mu nabla mu of minus 1 over square root of minus g delta of L hat delta g mu. Okay, so now I can also do, I did all of this for one of these terms in the variation of g mu nu. So there was this one term here, and I applied this manipulation to this one term. I can repeat the same arguments for the second term, and the result will be identical because of the symmetry of mu nu, g mu nu. So that if I apply it to the second term, I only change mu and nu, but because this is symmetry, I get the same answer. So that only puts a factor of 2 here. Okay, so therefore, this term here reduced to square root of g x I mu nabla nu of minus 2 over square root of minus g delta of L hat d of L hat d g mu nu. Now, what do we want to say? What we can say, so this sum has to be 0. This is always 0. It's just a symmetry of action. It's, in other words, it's an off-shell statement. Now, if I imagine that we go on shell, meaning that the fields psi satisfy the equations of motion, then on the equations of motion, this term vanishes. This is exactly what we do when we do a variation with respect to the field. Now here is where it's important that I'm applying this argument to the full matter action, because if I separate this Sm into S1 plus S2, and for instance both S1 and S2 depend on some field psi, then the variation of any single one of them would not vanish with respect to psi. So if let's say if this L hat is made of L hat 1 plus L hat 2, then you can imagine a situation where both of them depend on the psi, and then we won't have delta L hat, delta psi. So what we have is that the sum of these two terms is equal to 0 on the equation of motion. But individually they might not vanish. So what is important here is that all of the dependence on the psi is inside this L hat. There is no dependence on the matter field in the gravitational part. Okay, so because of that, this term is equal to 0 on shell. Which means that on shell this term has to vanish, given that xc was some arbitrary vector. So we learned that del mu of minus 2 over square root of minus g dl hat dg mu nu is equal to 0. Now this is the object that I'm going to call the covariantly conserved the stress energy tensor. If you like, I can lower the indices using the metric. So this is something that we call T mu nu. Covariantly conserved T mu nu is a tensor, and this tensor has 0 covariant divergence. Of course, unshared. So this is unshared, and this is unshared. But it's easy to see that if we just go back to Minkowski space, what we obtain here, so this T mu nu is something that I obtained from the matter action, or matter Lagrangian. So it's something that depends on the matter field. It's easy to see that if we go back to Minkowski space, it reduces to the Noether stress energy tensor that we would construct. Or it would coincide with at least one of the Noether stress energy tensors, because usually there is some freedom to modify the stress energy tensor. So this will be one candidate.
The symmetric, actually.
Yes. Yeah, this one is symmetric, while the Noether stress energy tensor does not have to be symmetric. You can add improvement terms to it to make it symmetric. Yes.
When we use the classical solution for the equation of motion, the fact that we are in shell, at this point we left quantum field theory and start doing only classical mechanics with our equations and the quantity that energy stress tensor that we got.
Yes, this is the state. This is an unshelled statement, so classically it is true. And then if you want to consider, if you want to ask what happens in quantum mechanically, then the statement would be that, for instance, the expectation values of this operator is 0, or this is 0 inside the expectation values up to maybe some local, some contact terms. But yeah, for the moment we are actually mainly concerned with classical field theory. So yeah, this is a classical state. Now, this way of deriving the energy momentum tensor is actually this is a very useful derivation, even if we don't care about gravity, even if we are talking about some field theory in the absence of gravity. Still, this is a nice trick to derive a conserved energy momentum tensor for that field theory. What do? We just follow these prescriptions to take that field theory and copy it to the metric to make the whole action generally covariant. That we can always do, regardless of whether we have gravity or not gravity. We just follow this set of tricks. Then we take the variation of the resulting Lagrangian density with respect to the metric, and then at the end we can set G mu nu to be eta mu nu. And all of the covariant derivative, we can reduce them to normal derivatives. So you just introduce this G, do the variation, and then you set it to be Minkowski. But you get this conserved symmetric conserved energy momentum tensor. Yeah.
We beforehand know that G mu nu couples to the all matter energy momentum sources the same way. At the end, using this, we end up one T mu nu that is related to the matter T mu nu.
I didn't understand.
We do this, but what we calculate is some variation of Lagrangian according to the metric. We end up with T mu nu, and this T mu nu shows us the matter and the matter energy momentum.
Yes, yeah.
Well, okay. So, did we hiddenly assume that G mu nu couples every kind of field energy momentum the same way, or even without assuming this, we would end up with the T mu nu of all the fields that are inside?
Well, we didn't assume it. It's just automatic. Remember what, if you like, what was the original way we got here? The original way was that we had this H mu nu, which on which we had to impose some extra symmetry. We identified that extra symmetry, that linearity homomorphism, with translations, with the space-time translations, which have now been made local transformers. We made that identification, and then everything follows from that. This universality of the coupling is just the consequence of the fact that the symmetry that your matter action had before talking about gravity was the global transformation of coordinates on everything, not separately. Like, you couldn't do different translations for different fields. Once you translate everything together, then you have the symmetry. Okay, so we have the covariant, the conserved energy momentum tensor. So if you remember, in the last session we talked about how to iteratively construct this theory, nonlinear theory of the spin 2 gravity. We said that we have to, once we put the zeroth order T mu nu for the matter, we have to keep adding terms to that. And those terms that we were adding had they were of two types. Some of them were purely gravitational. They only knew about H mu nu. The other ones were contain matter fields. So one should really think about this T mu nu that we get here is as the sum of all of the matter contributions to that expression. And now we are going to talk about the sum of all of the purely gravitational ones. Yes.
By doing this way, are we using the solution of the classical field theory for the graviton, and we impose our quantum field theory that we was constructing to that solution? So we impose that action to satisfy that solution. We're just using this fact here, right?
I didn't understand the question.
Like we was constructing, when we do this, when we assume that this is the sum of all the contributions of matter energy momentum tensor, I
didn't assume that, I claimed that.
how to climb that? I mean, because you have two sides, you need to make them equal. So you need to compute each of them and then show at the end that they are equal. Right.
Well, maybe if I talk about the gravitational part, then you see more clearly why this. Yeah, let's also talk about that, and then we put all of them together. So yeah, let us talk about this S gravity of h mu nu. But of course now we learn that we are supposed to put this h mu nu inside the full metric. So what are the conditions to construct this gravitational sector? The condition is as before. We want it to be generally covariant, be invariant under this diffeomorphism. So it should satisfy this symmetry. It is fully constructed out of the metric, does not depend on the matter field. And if I linearize in if I look at the quadratic part in h mu nu, it should reproduce what we had before for the quadratic action. So remember, we had some quadratic action for h mu nu that would give us the linearized equations for this spin 2 gravity. So that we had some S2 gravitation which looked like so I think it was something like minus 1 over 32 pi g integral d4x d mu h alpha beta d mu h alpha beta or some other terms. So this variation gives us the linearized equation that we have. And this expression that we wrote here was of course fixed completely by the requirement of invariance under linearized diffeomorphisms. Now what we want to do is to construct some nonlinear expression which is invariant under the full coordinate transformations, and such that when we perturb it, when we expand it at second order, it reduces to this expression. Right, so these are the two requirements: general covariance and matching with this quadratic. These two requirements completely fix this to be 1 over what do you say? 1 over 16 pi g integral d4x square root of g times r, which is called the Einstein-Hilbert action. What is r? R is just something made of the metric. So R is called the Ricci scalar, which is equal to the trace of Ricci tensor R mu nu. And Ricci tensor R mu nu itself is defined in terms of some other tensor called the Riemann tensor. Now what is Riemann tensor? Riemann tensor is a rank 4 tensor, as you can see, which is constructed out of the derivatives of this Christoffel symbol. So at the end of the day, it's just some expression, some second derivative expression in terms of the metric. So this is what it's like. And the alpha of gamma mu nu beta minus is antisymmetry under the exchange of alpha and beta. So there are linear terms in gamma, and then there will be nonlinear terms. Gamma mu, alpha lambda, gamma lambda nu, beta minus gamma mu, beta lambda, gamma lambda nu. Doesn't really matter, this expression, except that, at least at this point, except that if you remember that gamma itself is first related to the first derivative of the metric, that implies that this Riemann is some expression in terms of the metric that contains two derivatives. So in every term of this expression, if you expand it, plug in gamma, at every term there are two derivatives. And similarly, when I do these contractions, this property remains the same. So this Einstein-Hilbert action is just a generally covariant expression with two derivatives in every term. And it also has this property, or this coefficient is chosen, that if I expand this to second order in h mu nu, up to total derivatives, it reduces to what we had before. Now, but later we will see how to arrive at this expression, how to construct this. This is some exercise in differential geometry that they will learn in the future. But for now, just accept it that this is the unique expression that satisfies my two requirements, reducing to this and being generally covariant.
I have a question about the prescription. When we talked about the linearized transformations, linearized in the order of h, the transformations were in the coordinates from x to x minus kc, or whatever that is. That caused the metric to be transforming like the gauge transform that we proposed.
Yeah.
So when we go to the full nonlinear scale, considering all the orders, then this transformation is just changed from standard derivatives to covariant derivatives, right?
Yes. Yeah.
So, like, is it like that obvious, or is it something that one should carefully work out for?
Is it obvious? Well, at the end of the day, given that the metric is a tensor, a rank 2 tensor, is kind of obvious. But it is, it has a derivation that you can actually derive it. Do I derive it in the notes? At least there is an exercise. Maybe there is no solution for the exercise. But yeah, you can derive that transformation. So, I mean, what is the? There's no ambiguity, right? We have fully fixed everything. So we have said what is the transformation of the metric G mu nu tilde of x tilde is equal to dx alpha, dx tilde mu, dx beta, dx tilde nu, g alpha beta of x. So if I take x tilde and x to be related like that, I will get a linearized in this exact. Yes, yeah, we are linear. That thing that I wrote, that is the linear transformation. So it's a if I linearize in xi but do not linearize in h mu nu, then I will get the expression with covariant derivative.
So it is still linearized in psi.
Yes, yes, yes.
Okay.
I mean, you can more or less see how it's gonna work. There are some terms in here that you wouldn't have it when you only talked about these linearized diffs, because at that point originally when we were talking about linearized theory, we didn't identify these XCV translations. So for instance, there was never a term in the transformation. So in the transformation h mu nu, if you remember, there was xi nu, d mu xi nu plus d nu xi nu. Now once you identify this parameter to be the parameter of a space-time translation, there will be an extra term here, which is xi alpha d alpha of h mu nu. That was never appearing in our earlier discussion, because this is we were working to lowest order in h mu nu, so this would be a subleading term. But now once you include all of these kind of terms, it's still linear in xi. You will get delta g mu nu equals nabla mu xi nu.
The extra term proportional to the derivative of the metric is producing the Christoffel symbols.
Yes. Yes. Okay, so now we have the gravitational action. What we can do is to vary with respect to the metric. So if we take the variation, and I do the variation in a similar way as I did it in the derivation of the energy momentum tensor. If I look at 2 over square root of minus g, this is just some prefactor, it doesn't really matter. It's just there for the final result to look nicer. Another thing is that when I do derivation, sometimes I write Lagrangian, sometimes I write the action, but I always mean the same thing. So what we do is the usual thing. We take the metric, we do a small variation, linearizing that. We see what is multiplying that delta g mu nu. That would be the equation most. So if we do this, what do we get? We get 1 over 8 pi g. Again, this at this moment, the derivation of this might look terribly complicated. So just accept it. Later, we will see a relatively compact derivation of the result that I'm going to write. So when I do this, what I'm going to get is related to this Ricci tensor. So the answer is r mu nu minus 1/2 g mu nu r. And this whole thing is called the Einstein tensor. So this is called 1 over 8 pi g times g mu nu. Now, if you apply this derivation to the full action, of course, if I want to derive the equation of motion for the metric, I should vary the full action with respect to g mu nu. So if I apply this to the full action, there will be another piece coming from the matter action, and that's exactly what we call T mu nu. Right? So if we do the full variation, the Einstein-Hilbert plus matter, then this has to be equal to 0. This is imposing the this is the way we derive the equation of motion. We ask the variation of the action to vanish. So from the Einstein-Hilbert part, we get the Einstein tensor, this big g mu nu divided by 8 pi g. And from the matter action, we get T mu nu. So if I just move the terms to the other side of the equation, I get the Einstein equation, minus 8 pi g times T mu nu. Let me just comment again, because this notation might be confusing. This g is, of course, in g Newton is just a constant. But this g is this particular combination of the Ricci tensor and Ricci scalar. Now again, we have to ask the question about the consistency of this equation that we derive, or its agreement with the linearized theory that we have. And of course, once I said that at quadratic order, this action reduces to the quadratic action as we have, then we are guaranteed that at linearized level, this Einstein tensor is going to reduce to the linearized equation for h mu nu that we had. And indeed, it's the case. So if I linearize this g mu nu, so this g mu nu is a two-derivative object that depends on the metric. Only depends on the metric. Now we can again ask what happens if h mu nu is small. So if the metric is close to Minkowski, then we can expand this g mu nu. There will be a linear term in that expansion, and that linear term is just 1/2 the times the linearized equations that we have. That I just showed it for brevity with this tensor, this differential operator. And of course, this T mu nu that we have on the right hand, so that is also something that if I set something that depends on the matter field. Now, if I just set h mu nu to 0 on the right hand side, I will just get the energy momentum tensor of the matter field. Now, one thing that we can do maybe to just make connection with the story that we had at the beginning of the last lecture is that we can write this, we can decompose this g mu nu into the linear part and the non-linear part. So this g mu nu, I can just write it as g mu nu linearized or first order component plus g mu nu nonlinear. I'll just decompose it into these two pieces. And I can take this nonlinear piece to the right hand side. So then what do we have? We have G mu nu first order equals minus 8 pi G times T mu nu plus 1 over 8 pi G G mu nu nonlinear. Now, how can we think about? Let's now write some expressions for this T mu nu, for this G mu nu nonlinear. Let's expand them in terms of H mu nu. So this T mu nu, which was the matter energy momentum tensor, that starts from zeroth order in H mu nu. Even if I say H mu nu to 0, there will be matter fields in it. So this starts from a zeroth order term, and then there will be higher order terms in here. There will be corrections. And that 1 over 8 pi G G mu nu nonlinear, that by definition starts from second order in H mu nu, because I already subtracted the first order part. So this is something that starts from second order, and I will call it T mu nu with little t. So that what we have done here is that we basically achieved the expression that we were looking for at the beginning of the previous lecture. We said that we have the linearized equation, or linearized homogeneous equation for H mu nu with the property that it is ordinarily conserved, as it's identically conserved. So if I act by a derivative on this expression, it gives 0, and therefore whatever we write on the right hand side should also satisfy that property. We saw that in order to satisfy that property, we should keep adding corrections to what we wrote originally. And when we add a correction, we have to modify the action, and we need, once modify the action, there will be new correction, and we have to keep going. And of course, we didn't do that, but the promise was that we find a rule, we find some trick to construct that full nonlinear theory that would be the result of this summing all of those things. And this is that nonlinear theory. So this is the original term that we have on the right hand side, and then there are corrections of this one. Of course, now this equation is satisfied. The first derivative. The first derivative of this expression is equal to 0 on the equations of motion. But basically, more or less, because the first derivative of this is 0, identically. Yeah, and it was unique in the sense that we didn't have much choice in constructing this Einstein-Hilbert action. That was the only thing that would satisfy. But that I didn't show, but I will show it later. That's the only object that satisfies this requirement. Unless we want to put higher derivative terms in the equation. So, yeah, no, maybe, I don't know, did I answer or you still have the question?
I will look carefully at the big picture after that. So, but yes, it's
okay. So one last thing to discuss is whether we have some conserved energy and momentum that we can associate to some solution. So before we saw that if we have some conserved energy momentum tensor, when we were discussing nodal theorem, we defined some conserved charges. In the case of the space-time translation, we defined a conserved 4 vector, which was the integral of d4x t mu 0. This t was the nodal current. And the reason why this was conserved was that if I take the time derivative of this p mu, and I use if I can use if this t mu nu is conserved ordinarily, meaning that the ordinary derivative d nu of t nu mu is equal to 0. By the way, this is equal to d0 of t0 mu plus di of ti mu. So if this is equal to 0, then we can feed it in here, and that becomes d4x minus d4x di of ti0. Oh, sorry, this was d3x. We define our conserved charge by integrating the zeroth component of the conserved current on some slice, some spatial slice, not over the full space. But if I integrate over the full space-time, it doesn't make much sense to talk about conservation, because the quantity that has to leave, when I say d0 of p mu, it should depend on time. So it has to have some time variable to talk about its conservation. So it wouldn't make sense to integrate something over the space-time, because then I cannot say it lives at that particular time. Yeah, so this is time, and this integral is taken on some fixed time, t and x. Yeah, this 3x. So then it becomes if I have if this tensor is conserved ordinarily, then we could use conservation law to reduce this to a divergence, and then the divergence would reduce the boundary term. So that would be minus integral dsi, where s is the area element of our boundary times t0r. And then if we assume that, and of course since this is over the whole space-time, I have to set r to infinity here. And then if we assume that there is no fluxes at infinity, then our whatever quantity that we had here, the momentum would be constant. The form momentum would be constant, so this would be 0 if there is no flux. Okay, now the question is that in our gravitational theory, can we have a similar thing? Can we associate an energy, conserve energy and momentum to the system? And now you can see that the natural candidate fails in this case. Because if I'm going to use, for instance, this T mu nu, the new T mu nu that we constructed, this new T mu nu is not ordinarily conserved, it is covariantly conserved. And covariantly conserved quantities are not good enough to give us a conserved charge. But it was crucial for this derivation that I have ordinary conservation, not covariant conservation. So therefore this doesn't work. And of course there is a deep reason for that not working. Of course this T mu nu only contains, or not only, it contains both matter and the gravitational field. But if I set the matter field to 0, this vanishes. So in a sense this T mu nu takes care of the energy and momentum, or if it's going to define some energy and momentum, it would be something that has the energy and momentum of the matter field. But we know that the matter fields are coupled to the gravitational field. We can consider a binary system that loses energy into gravitational waves. And that energy in the gravitational waves is not included in here, because even if this gravitational waves travel away, where there is no matter field, and I still have energy stored in this gravitational field. That energy in the gravitational field we saw is in here, and perhaps in the higher order term. So it doesn't even make sense to try to find some conserved quantity. At least in full generality, it doesn't make sense to find a conserved quantity just based on that. If we imagine a situation, if we have the possibility of giving some of that energy in the matter fields to the gravitational field, it's similar to the case in which you have two fields which are coupled to each other. We couldn't find energy, conserve energy for them separately. The moment we couple the two systems, there will be only one total energy that is conserved. So this T mu nu is not a good object. Of course, similarly, just the sum of distance is not good. However, the sum of the two is a candidate for an ordinarily conserved energy momentum tensor. It's a candidate that we can use in this formula. And that is something that is called the pseudo tensor of energy and momentum. So this object, I can call it tau mu nu. And the property that it satisfies is that on the equation of motion, this tau mu nu is ordinarily conserved. In fact, that was our whole achievement, to find this object which is ordinarily conserved, and we can put it on the right hand side of this linearized equation. Now, why is it called a pseudo tensor? Because it is not a real tensor. If I under a general coordinate transformation, this full G mu nu acts like behaves like a tensor, and similarly this full T mu nu behaves like a tensor. But if I expand it and only keep the linear term, that linear term does not transform like a tensor on the general coordinate transformation. So for instance, if I'm going to plug that tau in this expression, if I try to plug that tau in this expression, what happens is that okay, so we have this tau, and that is our candidate here. However, this is a pseudo tensor, and what it means is that if I choose, now we can choose different coordinates or do different diffeomorphisms, and then this tau mu 0 will change. In particular, for instance, let's imagine we are away from the matter field. So we are only looking at this part, this second law. Then this is the part that only knows about h mu nu. Now, using these diffeomorphisms, we can, at any point, we can set that h mu nu to 0, and also its derivative to 0, which means that at any point we can just set this whole expression to 0 using some diffeomorphism, for some good choice of xc parameter that can be set to 0. And this is of course something that cannot happen for a tensor, because if all components of the tensor are 0 at one point, there will be 0 in all other coordinates. So this shows that it is a pseudo tensor. Now, then the question is that, is this expression well defined? Is it unambiguous? Because if it's going to depend on what choice we are making for the coordinate systems that we are using, it will be kind of useless. So again, this is I don't go too much into the details, but there is a relatively simple way to understand why it is well defined. And the way to understand it is that, as we see on the equations of motion, this tau mu nu is related to the linearized Einstein tensor. Now this linearized Einstein tensor has the property, so therefore in here I can replace this expression by minus 1 over 8 pi g integral d3x times g1 0 mu. This g1 0 mu has or g1 mu nu in general has the following interesting property. It's related to the fact that it is identically conserved. It can be written as the derivative of some other tensor. I just call it H, big H, alpha nu mu, where this H alpha mu nu is antisymmetric under the exchange of alpha and nu. So it is how does it look like? So it has, for instance, the alpha H mu mu minus okay, I don't write the whole thing. because I don't remember. But it is some, this G was a linear expression in h mu nu with two derivatives. And it has the following form. It can be written as d alpha of some other matrix, which is again, of course, linear in h mu nu, but with one derivative, because one derivative I extracted. It has the property that h alpha nu mu is equal to minus h nu alpha mu. So it is anti-symmetric under the exchange of these two. Of course, if I lower this index nu, this g mu nu has to be symmetric. So it has some nice symmetry properties. Although we don't care about that part at the moment. So it is anti-symmetric under the exchange of alpha and nu. And that guarantees that if I take another derivative, so if I take derivative d nu of g nu mu, it becomes d nu d alpha of h alpha nu mu, and derivatives commute with each other, but this is anti-symmetric, and that's how it is. This linearized g mu nu is identically conserved. So regardless of what is the solution for this little h mu nu, this is equal to 0 just because of the symmetry structure. Okay, so why do we care about this? We care because I can use this expression in here. So I have minus 1 over 8 pi g integral d3x, and here I should put the derivative d alpha of h alpha 0 mu. But since this h is anti-symmetric under the exchange of these two indices, and I fix one of them to be 0, this other one has to be a spatial index. It cannot be a time index. But now what do we have? We have some expression which is a total divergence, so it reduces to a boundary term. So we get minus 1 over 8 pi g integral over the boundary now this expression is much more tractable and useful because of the following fact. Because this h is a linear expression in h mu nu. So this is some order h mu nu object. Now, if I have some system which is even strongly gravitating, so that we have to use a nonlinear equations and stuff, we can still imagine the situation in which the system is asymptotically Minkowski. So far away from the sources, we go back to Minkowski space, which means that this h mu nu at large distances it goes to 0. When we go to these large distances, when h mu nu goes to 0, then we can linearize the metric, and we can use all of the machinery of the linearized theory. In particular, we get some expression which is invariant on the linearized diffeomorphism. So remember, this h was something that came from G1 mu nu. G1 mu nu was the unique expression that was invariant on the linearized diffeomorphism. And now we obtain some boundary term at large distances where we can linearize, and it is invariant on the linearized diffeomorphism. So no matter what we do, how we change the coordinates in the where the sources are, where the gravity is strong, as long as we require that asymptotically we remain Minkowski with the small deviations, then what we obtain remains invariant, doesn't change, because this H is invariant on the linearized things. Moreover, in this linearized regime, H mu nu was just a Lorentz tensor, rank 2 Lorentz tensor that lives on Minkowski spacetime. So now it's not surprising that the P mu that we get here is a Lorentz vector that lives on this asymptotic. So what we have achieved here is that we found a way to assign to some spacetime which might have large gravitational fields. We assign to this full spacetime a conserved energy and momentum. That is well defined. Yes.
G1 mu nu was not a tensor, was not transforming as a tensor, but when we redefined G1 in terms of the big H, we defined H as a tensor in terms of H mu nu, small h.
Well, G1 is not a tensor on the, if you do general coordinate transformations and your metric is not small, then G1 is not a tensor. So if it change by order, high order tensor, remember here for instance, there are this extra term. So this H mu nu was changing like that, plus this extra piece that was linear in H mu nu. So what happens for G1 is that if you consider the variation of G1 mu nu, it's not a tensor because this variation under some general coordinate transformation will be order H. And that order H will be cancelled. So now if we look at the full expression for G, if you do a coordinate transformation, there will be some order H term coming from here, which will be cancelled by some transformation in those nonlinear terms. So yes, it is not a tensor. Also, the same is true for this big H. Also, big H is not a tensor in this sense. However, if you go in the linear regime, when H is going to 0, then it acts like it is it's a Lorentz tensor, not a tensor on the general. Becomes a Lorentz tensor, not a tensor on the general coordinate transformation. And that's what we need here, because we want to assign to this asymptotically Minkowski spacetime a Lorentz vector P mu that lives in this asymptotic Minkowski space. So say if I'm an observer far away from a strongly gravitating system, I want to assign a 4 vector in my own Minkowski frame. I want to assign a 4 vector that represents the mass and momentum of that system. And this object does the job.
And this was another Lagrangian that somebody gave us at the first look. And I could use the Noether's current method to find some current. So if I use that, do I get something else, something meaningful?
Well, yes, because that was the object that, well, no derivation, no current, there is sometimes some ambiguity, so that it's not always unique. For instance, it doesn't have to be symmetric, but you can add some improvement terms to this energy tensor to make it symmetric. But essentially you are going to get this expression, which is what we used here. Because remember the original logic, we were looking for something that is ordinarily conserved, and that something can be obtained by applying the nodal theorem to the full action. So that was our original hypothetical strategy, to take the action, apply the nodal current, derive whatever conserved energy momentum tensor that we have and put it here. And after going through these tricks of constructing the action in a different way, at the end of the day we have this object which is ordinarily conserved. So in fact, if you apply the nodal theorem to the action, if you do it carefully, then that is what you are going to get.
The non-linear action that we now wrote, Einstein Hilbert action plus the matter action. If I do that procedure, that full action, I would end up with something like this, because we already built it through this series like that.
So what we have done so far is that no matter which system we are considering, if we are far enough, we can assign a conserved charge, meaning energy, to this system. But now if we cannot go far enough, like if we live inside of this system, let's say the universe, so is it a problem to define energy of the universe, let's say, in that sense?
Yes, it's not well defined in GR. So it's only when you have some fixed asymptotics that you can construct some well-defined conserved energy or well-defined mass, for instance, for a system.
But I think there is still this, I've heard of this thing that the 0,0 component of the energy tensor should be positively defined. At least we still have that. I mean, why is this important first, that the 0,0 component is positively defined? And
0,0 component of this T mu nu. Well, that is there is no proof of that. That's some expectation that we have, because the 0,0 component is like the energy density. So you normally expect healthy systems have positive energy density. But it's not really well. In fact, I can give you an example in which it's not the case, and it's perfectly fine. Just take a scalar field with a potential. If the potential of the scalar field goes negative, say your scalar field this is V of phi. If the potential, the bottom of the potential is negative, then T00 becomes negative. And it's not a surprise if the potential, you get negative potential energy. And there's nothing wrong with this system, except that if you want to put it in gravity, then it gives you untitled spacetime. And untitled spacetime crunches, but as a matter of principle, there's nothing wrong with it.
But observationally, the universe seems flat, meaning that the matter component produces positive gravity, whatever. So in our universe, we expect that the T00 component to be positive. Or isn't it? Or we don't know.
Well, the fact that it is, I mean, as I said, there are some expectations that this should happen, but we cannot rule out the possibility that somewhere T00 becomes negative, although in most places that we see it is positive. Like for instance, again, with this scale, if we imagine we have two minima. I suppose we live in here, so this is us. This is called a false vacuum of this theory. So we can be living in the false vacuum, and classically you live there forever. Quantum mechanically there is a chance of tunneling to the true vacuum, but that probability can be low enough that for the age of the universe we are not going to tunnel. Like say that the tunneling rate is much longer, or much smaller than 1 over the age of the universe. So from the fact that we saw positive energy, we cannot conclude that negative energy, negative T00 cannot happen. Maybe somewhere else, some civilization tunneled into the true vacuum, and then it collapsed into a singularity.
I have a small question, but the time is running down.
Okay, let me just